talk about moment of inertia. Here, we need to account for the kinetic energy of rotation of an object. We'll start by defining the mass distribution in the object, and use that to define a quantity called the moment of inertia. We'll finish by defining the rotational kinetic energy in terms of the object's moment of inertia. Let's consider a rotating object. Even if the object isn't moving, there's kinetic energy in the object because its particles are moving through space as they rotate around the axis. What we can do is start by defining point masses everywhere in the rotating object. Each one of those point masses has a radial distance from the axis of rotation. Each one of those point particles also has a velocity. The further from the rotation axis, the faster it's moving. All of these velocities are perpendicular to the radial position vectors. We can define the kinetic rotation energy as 1/2 mv1 squared plus 1/2 mv2 squared plus etc. all the way through all the massive particles in this object. Now, since it's rotating about an axis, we can write each of those velocities as r omega. They all have the same omega. They have different r's. So we write the rotational kinetic energy as 1/2 m1 r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus all of the other points. We can write this as a sum on I of mi ri squared. The rotational kinetic energy equals 1/2 the sum on I of mi ri squared omega squared. We define this sum of mi ri squared as the moment of inertia I. We can write the rotational kinetic energy as 1/2 I omega squared. If we have some distribution of matter that's continuous, we can write this sum as an integral. If we work through the integration of some common objects, we could find the moments of inertia. The moment of inertia of a thin rod about its end is 1/3 ml squared, where L is the length of the rod. The moment of inertia of a rod rotating about its center of mass is much smaller, 1/12 ml squared. The moment of inertia of a solid cylinder is 1/2 mr squared, where r is the radius of the cylinder, and a hollow cylinder has a moment of inertia of mr squared, while a solid sphere has a moment of inertia of 2/5 mr squared. The moment of inertia defines the mass distribution of an object. A larger moment of inertia means it's harder to start something turning. So think about those first two, the rod rotating about its end and the rod rotating about its middle. Pick up a pencil or some similar object nearby and rotate it about its end. You can feel it takes quite a bit of effort to turn it through the air. If you just hold it about its middle, it takes much less effort to turn it about its middle. That smaller moment of inertia means it's easier to turn. Let's look at a question that gets at that same concept. What if I had a solid sphere and a solid cylinder starting from rest? Let them roll down to the bottom of the ramp. Which one would reach the bottom first? Now remember, the solid sphere has mass further away from the center, so it has a higher moment of inertia. The sphere has a lower moment of inertia. That means that the cylinder would be harder to start it turning. The sphere is easier to start turning because it has more mass situated close to the rotation axis. The sphere would accelerate faster and reach the bottom faster. Moment of inertia is a measure of the mass distribution in a rotating object. The rotational kinetic energy can be written in terms of the moment of inertia. An object with mass distributed farther from the rotation axis has a higher moment of inertia. Let's use this concept to think about why a tightrope walker would carry a long bar. Seems kind of silly. It makes his mass bigger. Wouldn't it make it easier to tip? It actually increases his moment of inertia, making it harder for him to tip, making it easier to balance. I hope this helps you learn about moment of inertia. Thank you for coming. Please come again soon.